Hello and welcome to the same episode of How to Understand X that was just previously uploaded. I don't know how to stitch these two videos together, but my recording software decided to stop working. So we were working on the derivative of e to the power of x. Sorry for that. I probably should learn how to put these two together, but that requires effort, and we're not good at that. We were at the limit definition, so the limit as h approaches 0 of e to the power of x plus h minus e to the x all over h. Now from here, we have the same base, so we can split these into two. We have e to the x times e to the h minus e to the x. We factor out e to the x, and we can actually bring that out of the limit entirely. Then we have the limit as h approaches 0 of e to the h minus 1 over h. And now we say that a is equal to e to the h minus 1, and then we added 1, a plus 1 is equal to e to the h, which means that ln of a plus 1 is equal to h. So let's plug that in. We have a over ln, a plus 1. So now we can multiply both the numerator and the denominator. Oh, and we also said that as h approaches 0, ln of a plus 1 is approaching 0. So if you do e to the both sides, you have a plus 1 approaches 1, which means that a approaches 0. So this limit still works the same. We still have e to the x times the limit as a approaches 0 now. And then with this ln property, we can actually bring that as a power. Right? We can have ln of a plus 1 to the power of 1 over n. And now, since ln is a continuous function, we can put that limit inside the ln too. So we'll have e to the x times ln of the limit as a approaches 0 of all of that. And also, in that numerator, we have 1 over a times a, which is going to be 1. Right, those a's cancel. And now, the limit as a approaches 0, of a plus 1 to the 1 over, what is it, a? Yeah, that should be 1 over a. This is e, right? And then, well, that's one of the many definitions of e. There's a way to write e as a series and all sorts of stuff, but at the end we're going to have 1 over ln of e, which is 1. So we're going to have 1 over 1 times e to the x, which is just going to be e to the x, which means that the derivative is e to the x. Now, from that we can actually define the derivative of the natural logarithm y equals ln of x using implicit differentiation, as we said. Y equals ln x, which means that if we put both sides e to the power of, you'll have x is equal to, since e and ln are inverse operations, they'll cancel out, you'll have x is equal to e to the power of y. And now we can do d dx of both sides, d dx of x, and then d dx of y. Using chain rule, we know that y is a function of x, so we can do the derivative with respect to y multiplied by the derivative of y with respect to x. So we'll have e to the y times dy dx, and then, as we said, derivative of x is going to be 1. So, derivative with respect to y of e to the power of y, as we said, e to the power of x, that derivative is just e to the power of x. We have e to the power of y, and then we divide both sides by e to the power of y, so we get dy dx is equal to 1 over e to the y. And as we set up here, x equals e to the power of y, so dy dx is equal to 1 over x. So if y equals ln x, if you differentiate both sides with respect to x, you'll get dy dx is equal to ln x. Easy enough. So now we can have some fun, I think. What other important ones are there? I think that's, we do need to do a to the power of x. A to the power of x. Now, if a can be expressed as e to the ln a, right? It's kind of like saying square root of a squared, right? These are two inverse operations, the square root and the square. And so e to the power of ln is an inverse operation, and it'll cancel out. So you'll get e to the ln a is still equal to a. So let's write that one more time. We have a to the x is still equal to e to the ln a to the x. So now from here we can say that this is a function, right? This is e to the power of u. So let's set u equal ln a to the x. So now from here we can do, well, u prime, not ln a to the x. That would be a very different function. We have, well, technically it is ln a to the x, but with our like logarithm rules, we can actually make this x a factor. So we'd have ln a to the x is equal to x ln a. And now, if you differentiate this with respect to x, so if this is u, and you do du dx, ln a is going to be a constant, right? A is not a function. So if you have ln a, that would also be not a function, so a constant. And so you just do the derivative of x, which we said was 1, times ln a. So du dx is ln a, which means that u prime, I didn't know why I wrote du dx. Maybe I'm just thinking of, what's it called? Integrals too much, but we do eu times u prime, right? We have to do f prime g of x times g prime x when we see a function inside of a function. We do the derivative of the outside, so differentiate f with respect to f, and then multiply it by the derivative of g. So, from there, we just plug in what we have. We have e to the power of u, right, which is e ln a to the power of x. And from here, we have u prime, which we said was ln a. So derivative of e to the u, d dx of e to the u, is going to be equal to e to the u times u prime. Again, derivative of the outside times derivative of the inside. So same kind of principles behind it. And then the e to the ln ax, e and ln, opposite operation, so we have a to the x times ln a. And that's, normal and all. And now we can get into the crazier derivatives. I'm just going to search up derivative practice, and hopefully we get some interesting stuff. Okay, we'll start off, relatively normal. We'll have y equals sine 2x, and we have to find dy dx. Okay, so we have a function inside our function. We have 2x, right? And so we have to do u is equal to 2x, which means that u prime is equal to 2. So we do the derivative of the outside times the derivative of the inside. So derivative of sine, we said that was cosine 2x times u prime, so that's going to be times 2. So this will be 2 cosine 2x. Okay, and then we just, I think we'll stop there for that one. Something's wrong with the formatting of that question, but okay, we have an interesting one. We have arcsine of cosine x. Y equals arcsine of cosine x. Alright, function inside of a function. This is going to be normal chain rule, so we'll have u cosine x, which means that u prime will equal negative sine x. And from here, and even though I said I wasn't going to show this derivative, I'm going to show it because, it's fun. So we have y equals, I'll put some space for that, y equals arcsine x. So we'll just do sine of both sides. Again, I told you these are very similar proofs like the one that we did back a little while ago, sine of sine will cancel out. Inverse operations, we have sine y equals x. So now we do derivative with respect to x on both sides, and then we get cosine y dy dx. That means that, and derivative of x is just going to be 1. Again, we had to do d dy of sine y times dy dx, chain rule, because y is not explicitly defined as a function of x. So now when we solve for dy dx, we get 1 over cosine y. And now let's draw that triangle. We said that y is an angle, and sine y equals x. So x over 1, and then, so we have the opposite, so sine over hypotenuse, and if sine y equals x, that means that sine y is equal to x over 1, which means that 1's the hypotenuse and x is a leg, and so we do x squared plus a squared equals 1 squared, so we have a squared is equal to 1 minus x squared, which means that a is equal to the square root of 1 minus x squared. And now 1 over cosine y, that will just be, if this is cosine, so adjacent over hypotenuse, adjacent is square root of 1 minus x squared over 1, so cosine y will just be that side, so you do 1 over that side, you get 1 over square root of 1 minus x squared. Now from here, we just plug that in, right? We have, so if the derivative of the outside function is 1 over square root of 1 minus x squared, the input is not x, the input is cosine x, right? So you can actually, since we're using u notation, we can say that this will be u squared times u prime. We had to change this cosine x to u, and then now we say that this is negative sine x over square root of 1 minus cosine squared x. I'm not sure if this simplifies, nicer than that. I think you could actually make a case that it would look like, so you have sine squared plus cosine squared x is equal to 1. So if you have 1 minus cosine squared, you'll get sine squared, right? That's what will be left. So you'll have the square root of sine squared, which will be positive sine squared, or the absolute value of sine. Oh, if you do the square root of sine squared, you'll get the absolute value of sine. So you'll have negative sine x over the absolute value of sine. I'm not sure if this evaluates to 1 or not, though. I think it'll just be absolute value. Like, it'll just oscillate between 1 and negative 1. But, yeah. It'll be absolute value for square root of a squared trig. But let's go into some more examples. We have we have second order of x ln x. So if this is f of x, we have to do the second derivative. So f prime x and then f prime prime x. So if we have x ln x, we do product rule, which means you do derivative of this times that, and then plus this times derivative of this. So we have x prime times ln x plus x times ln x prime. And now this one we said was 1 over x, and we said this one's 1, so x ln x, x prime ln x is going to be ln x, 1 times ln x, plus x times 1 over x, so that'll be a 1. And then this one will be nice and easy. We have derivative of a constant, which is 0. I've said this many times, but if you have a constant function, like say y equals 1 for this one, and you plug some tangent line, if you plug in at any point and try to find the tangent line, the slope of that tangent line will always be 0. These will be horizontal because the line itself is horizontal. And so f double prime will be 1 over x plus 0, so plus nothing. So yeah, that was okay. Now we have local minimum. Okay, this one is might have to do the first derivative or the second derivative test, but let's talk about what those mean. So the derivative test is, well, let's talk about what the derivative represents. It's the instantaneous rate of change, right? We said that at any point on a curve, if you could find the derivative, this is in the first derivative video that I made, if you could find a derivative of any point, like say right here, this is the slope of a line that just touches, right? If we zoom in really, really close, it's like the average rate of change between 2 points that are extremely close to one another. And if the average rate of change between two extremely close points is 0, like right about that point, that means you have a horizontal tangent, or the derivative will equal 0, which means that the derivative can equal 0 at these minimums or maximums, right? If you draw lines that just touch at the minimum or a maximum, then you will get 0. And but those aren't the only cases. There are also just normal horizontal tangents. Like if you look at the derivative of x to the power of 3, let's do that one real quick. We have n is equal to 3, so 3x times n minus 1, so 3 minus 1 is 2. And if you try to set this equal to 0, right, we want this to equal 0, and, well, let's solve for it. You divide both sides by 3, 3, you get x squared equals 0, square root of x, square root of 0, x will equal 0. But when you plug in x to the power of 3, when you plug in x to the power of 3 into some kind of calculator, or if you just graph the points yourself, you'll see it just kind of goes straight through. That's because it's kind of like a bumper car. You know, like, it's bumping, it's just going through the point. It's like, it's kind of having a minimum and a maximum at the exact same time. This is a repeated route, right? So when you kind of go through, it's like it's kind of bumping very, very quickly. But that is not a minimum nor a maximum. It's happening instantaneously. But that's just kind of how I think of it. Horizontal tangents, like the one at x cubed at x equals 0, is not a minimum and not a maximum. So how can we just know this? How can we know certain things about functions without actually being able to like graph them? Say we have to do it by ourselves. So let's see y equals, the function that we're given is y equals 1 over x and then plus x. We are trying to find the local minimum. So let's try to find y prime. Y prime will equal, this is x to the negative 1. So let me rewrite this. We have x to the negative 1 plus x. So n is equal to negative 1. We can pull that negative. And then n minus 1 will be negative 1 minus 1, so minus 2. Plus derivative of x we said was 1. So we have negative 1 over x squared plus 1. And now we have to have this equal 0. So negative 1 over x squared plus 1 equals 0. Let's just bring the x's on one side and the numbers on the other side. And now we can just divide both sides by negative 1. Then you multiply x squared to this side, you'll get x squared equals 1. Which means that x is equal to plus or minus 1, right? And from here, we can't say we're done. We don't actually know if plus or minus 1 are minimums or not. We just know that the derivative at that point equals 0. We don't know if this is maximum, if it's a minimum, if it's one of those horizontal tangents that we saw like at y equals x cubed. So we need to do something else. And that is, well, let's talk about what the derivative means in the context if you know the derivative but you don't know the actual graph. So let's draw a curve, right? And let's draw a point there, and this is the tangent line at that point. This tangent line has a positive slope. that means that the average rate of change between 2 points that are very, very, very close together at that one point, or the instantaneous rate of change at that one point, is positive. So that means that the slope, if the slope is positive, or the derivative is positive, that means that the function is increasing. Derivative is positive, greater than 0, then f is increasing. And that makes sense, right? I mean, you see that the tangent line, the slope of a line that just touches at that one point, the slope of that line is positive. So the rate of change at that one point is positive. So the actual function itself is increasing. And again, if you think back to average rate of change and how like instantaneous rate of change is like average rate of change, except with 2 points that are like so close to one another that they're basically the same, like the limit as c approaches 0 of x plus c and x, these two values are obviously very, very close to one another. And if you directly substitute, you'll just get them, but c is only approaching 0, which, leads to some other stuff. But if you just think of it as like the average rate of change between 2 points that are incredibly close together, then if you remember, average rate of change came from slope. It came from the slope of 2 points, like linear slope, y equals mx plus b, that kind of slope. And you said that if the slope is positive, and that line is increasing, and if the slope is negative, then the line is decreasing, right? Like if we go back to y equals x and y equals negative x, the slope would be negative, right? M would be negative, and this function is actually decreasing as x approaches infinity. Worst possible infinity I think I've ever drawn. Hold on. As x approaches infinity, y will approach negative infinity, right? So on that interval of all x, y will be decreasing. And that's because the slope between those 2 points on that line was negative. And if the function is increasing, that means the slope is positive. So the positive slope of a tangent line means that if the derivative is greater than 0, then f is increasing. Let's draw another point and let's draw another tangent line. It'll look like that, right? Obviously it's not touching, but if it was touching, the slope of that line would be negative, right? And the function itself, the function is decreasing at that point. So the slope of a line that connects two incredibly close lines on some, larger subinterval, that that subinterval, it's decreasing on that subinterval because the derivative is less than 0. Derivative is less than 0. So f is decreasing. I'm hoping that makes sense. I feel like I'm going a little bit fast, but just remember, you have the slope of a line that just touches, right? And if the slope of that line, that's what the instantaneous rate of change is. That's what the derivative is, the slope of the tangent line. And the tangent line is just, again, a line that quote-unquote just touches, but it technically just connects two incredibly close lines, incredibly close points on a curve. But if the slope of that tangent line is positive, that means that the function's increasing, right? Because the instantaneous rate of change at that point, or the slope of a line that just touches, is positive. I feel like I'm repeating. It's not circular, I promise, but if the slope of the tangent line is positive, then the change on that interval, that very small subinterval, is positive, which means that the function is increasing at that point. And if the derivative is less than 0, if the instantaneous rate of change or the slope of that tangent line is negative, that means that on that subinterval, f is decreasing. The slope of that line is negative. So yeah, I'm hoping that makes some sense. And now let's talk about the second derivative. What does that mean? Actually, let me keep that. So imagine that this graph, this was originally f of x, but let's say that this was f prime x, right? Let's say that this was the graph of some derivative. And we are trying to find the f double prime, or like the second derivative. Same idea. The derivative is greater than 0 at that point right there, the one that we highlighted. The derivative is greater than 0, and f prime will be increasing for the same reason that f was increasing when the first derivative was increasing. When the first derivative was positive, regular f was increasing, and now that f double prime is greater than 0, f prime is increasing. So same logic, we're just changing it slightly, using f prime instead of f. So, all is normal. But what's important here to know is that this means that when the derivative, or the second derivative, is greater than 0, that means that the graph is concave up. That means that f is increasing at an increasing rate. So if we're increasing at an increasing rate, you can also think of it as the tangent line is kind of, how should I say this? It's increasing at the same rate that like you are traveling at. Okay, so I'm gonna actually try and illustrate this. So let's have a nice and simple parabola, right? And I'll start with concave up. So if we draw a parabola like that, it's a very sad parabola. But if you draw tangent lines randomly, right? Let's draw a bunch of tangent lines. They're not very well done. But if you draw these tangent lines, you're seeing that as this interval continues, the slope of this tangent line is increasing. It's going from negative to 0 to positive, right? It's decreasing, or not decreasing, but it's negative, and it's continually negative, but it's starting to decrease, not decrease, it's starting to increase, then it becomes 0, then it increases, and then it continues to increase. This is concave up, which means that the derivative is increasing. Concave up, you can also think of it as that parabola. It's opening upward. If you draw tangent lines at every single point, the tangent line will slowly be increasing until, it's positive. And if you look at the concave down, or when the derivative, or the second derivative is less than 0, so f prime is decreasing, f prime is actually not increasing. So you can, I'll try to make these lines a little bit more dramatic so you can see what I'm talking about. We have this parabola, right? And then you have, I'll make it a little bit more dramatic, even though this isn't, accurate. Let's say that these are the tangent lines, right? The tangent line is slowly but surely increasing. I don't know how to really describe this. So we have this. I should not even put axes. I'll just put the parabola, and then I'll try to draw it. So you have this concave up, right? And these lines, they're very negative, then they're slightly less negative, and they're even less negative, until they get to 0, and they're not negative, and then they are positive, and then they're more positive, and then they are, super positive. So on this interval, this negative is continually becoming less and less negative until you get to just 0, in which case it starts going more and more positive until, it's fully positive. As you can see, the slope is slowly but surely increasing. So since the slope is increasing, this second derivative is positive, greater than 0, which means that the entire graph, original f, is concave up. Now let's try and draw concave down. So concave down, we'll say that this is, let's draw, it's slowly but surely decreasing, right? Let's keep drawing these. So if you draw off to the side, this is the slope of one tangent line, and it starts out very positive, but as you go up, or it starts, bending downwards, as you go further along this interval, the tangent line, that slope actually decreases to the point where it gets to 0, and then it actively becomes negative. So yeah, I mean, if you get what I'm saying, I know it's a bit of an abstract idea, but this slope, this tangent line, the tangent line at every single point, and this is f prime, right? This is, well, this isn't f prime, but this is f, and we are graphing f prime, and then we are talking about f double prime. We're seeing how this f double prime is less than 0, which means that each of these points, each of these tangent lines are slowly but surely decreasing, which means that the second derivative is less than 0, and the graph is concave down. So, just to sum up, when the first derivative is greater than 0, f is increasing. Let's even write down this because this is important. When f prime is greater than 0, f is increasing. When f is less than 0, or f prime is less than 0, f is decreasing. When f prime equals 0, we have horizontal tangent. Alright, and then when f prime, or f double prime is greater than 0, we have a concave up. And then when f double prime is less than 0, we have a concave down. Alright, concave down. And now from here, we can actually do something very interesting. We know that if f prime 0, we have a horizontal tangent, right? We already know that it's either a relative, well, it's not either, it can either be a relative max, a relative min, or a local max or local min, or it can be nothing. It can just be that horizontal tangent. But if we know for certain that f double prime is greater than 0, so it's concave up, and we know that the horizontal tangent is equal to 0, then this point will be a relative minimum, right? We know that this graph is concave down, which means that each of these tangent lines are slowly but surely increasing. It goes from negative, slightly less negative, till you get to 0, then it goes positive, even more positive, etc. And if you have all of that, and so f double prime is greater than 0, so it's concave up, and you have f prime equals 0, then there is a relative minimum. And say that, f is concave down, which means that the slope of these tangent lines, they go from extremely positive to slightly less positive to 0 to negative to more negative, and on and on. So f double prime is decreasing, or not decreasing, but it's negative, so f prime is decreasing. Then if you said that that was a tangent, a horizontal tangent, which means that y prime or f prime is equal to 0, that means that at that point, when f double prime is less than 0, so the graph is concave down, that is a relative maximum. So I'm hoping, I know I'm going a little bit quick, but I'm hoping that you can see that if f prime is greater than 0, f is increasing, because f prime is the slope of the tangent line. And if the tangent line, or the point or the line that just touches at a specific point, is increasing, or if it has a positive slope, that means that f, the original function, is increasing. And if the slope of the tangent line is less than 0, then on that interval the function is decreasing. And if f prime equals 0, that is a horizontal tangent. And if f double prime is greater than 0, that's concave up, which means that the slopes of the tangent line, they are slowly but surely increasing. If you have a horizontal tangent and it is concave up. So let's draw that one more time. You have a horizontal tangent and it is concave up. This is a relative min. If you have a concave down, and a horizontal tangent, that will be a relative max. So yeah, let's go back to our original equation. I feel like I should have said that during my actual derivative video, but I guess that's life. Where am I going with this? I wasn't going anywhere. Okay, so we have x equals negative or plus or minus 1, right? This is when the derivative is greater than or not when the derivative is equal to 0. So we know that f prime equals 0 when x equals plus or minus 1. Now, if we do the second derivative, because we're trying to find the local minimum, remember local or relative min? So if we know when these two values are those values, f prime x is equal to 0, there is a horizontal tangent, then if f double prime is greater than 0, if we have a concave up graph like that, then you will have a minimum right there. So let's do the second derivative really quickly. We have n equals -2, so we can bring that out. We have negative times negative, so positive 2 times x to the -2 minus 1, so -3, and then derivative of 1 will be 0. So we have 2 times x to the -3, or 2 over x cubed. And now let's plug in x equals -1, x equals positive 1. So you'll have 2 over positive 1, so 2. And then 2 over -1 will be -2. So at x equals 1, let's write this down. At x equals 1, we have f double prime is greater than 0, right? It is positive 2, which means that it is concave up. And since we know that f prime is a horizontal tangent, that means that this is a relative minimum. At x equals -1, we have f double prime is less than 0, right? F double prime is less than 0, which means that the graph is concave down, which means that that point will be a relative maximum. Because we know that this is a horizontal tangent, and we know that the graph is concave down at that point. I'm hoping that makes sense, but yeah, x equals 1 is where we do have a relative minimum, and we can go on to our next problem. I'm hoping we get more second derivative and first derivative tests, because we do need a little bit of practice in that. Alright, speak of the devil, the next question that we have is also going to be a local minimum one. We have f of x is equal to sine x plus cosine x. So f prime x, we did these derivatives a little while ago. Derivative of sine x is cosine x, and derivative of cosine x is negative sine x. Okay? Now, we need to set this equal to 0. So when does sine x equal cosine x? I'm just, bringing the sine x to the other side, and then swapping the order, because I like to have sine on one side, or the left side, and then cosine on the other. Well, there are a couple values where this exists. We can even draw this really quickly. Sine will equal cosine in the third and first quadrants, I think. So it's definitely here, right? And here, sine, so y, is negative, and cosine is negative as well. So yeah, quadrant 3, you have minus, minus, plus, and then second quadrant is plus, minus, minus, then you have minus, plus, minus, then you have plus, plus, plus. Those are just the signs for sine, cosine, and tangent, because sine corresponds to y, and then cosine corresponds to x. So if you have everything on the positive x-axis, so the second will be positive, and everything on the negative, everything on the negative x-axis, this side, will have negatives for their second values, and then everything in the top half will have a plus, right? Plus, plus, and then everything in the bottom half, I'm circling a lot, but everything in the bottom half will have minuses for their first values. And then since tan is equal to sine over cosine, you just adjust your signs accordingly. But it'll be first and third quadrants, so we can plug those values in. Sine x equals cosine x when, okay, I can show the work for this. Sine over cosine, and we do cosine over cosine. So we get tangent x equals 1. And we do arctan on both sides. We have x is equal to arctan 1. Right? And then this is in the first or third quadrant. So we have, let's draw our unit circle again. We have pi over 4. That's in the first quadrant. This is the arctan of 1, by the way. Pi over 4, 3 pi over 4, and then 5 pi over 4. And of course 7 pi over 4, but these are the two ones that we need to care about. Pi over 4, and then 5 pi over 4. Okay, so from here, let's do the second derivative, because we know that at these two values, this function will be, well, the derivative of this function will be equal to 0, so we'll do f double prime of x. We say derivative of cosine is negative sine, and then derivative of sine is negative cosine. I mean, derivative of sine is cosine, so this negative will be negative cosine. And now let's plug in pi over 4. You'll get negative root 2 over 2 minus negative root 2 over 2. We don't even need to do any work past that, even though we will because it's fun. Root 2 minus root 2 will be, negative minus negative will be negative 2 root 2. And then you have that over 2, so you'll have negative root 2. But automatically when you saw this minus and a minus, we know that this will be a negative number. So this will not be a local minimum. And let's look at the f at sine minus cosine. When you plug in 5 pi over 4, you get positive root over 2 because sine of 5 pi over 4 is going to be negative root over 2. So this will cancel out with the already existing negative. So plus, and then cosine 5 pi over 4 will also be positive root 2 over 2. Or it'll be negative root 2 over 2, but negative and negative will cancel out. So now we have positive root 2, which means that the graph is concave up, which means that that will be a local minimum. Oh, wait, it's asking for local maximum. Never mind. Yeah, on me. But we know that derivative of second derivative at pi over 4 was equal to negative root 2. So this will be less than 0, which means that the graph is concave up, concave down. And then, okay, I can draw this horizontal tangent will be at pi over 4. So this will be a local maximum. And it wants us to get the actual point, so we plug pi over 4 back into this, f of x. So sine pi over 4 was still root 2 over 2, plus cosine pi over 4, still root 2 over 2. So we get root 2 over 2 plus root 2 over 2 will be 2 root 2 over 2, which is going to be just root 2. Let's see if we got this one right. Okay. Interesting. Okay, so this is like a word problem. So I'm not going to write it out, but it says that if the function f of x contains a local maximum at x equals c, then f double prime of c will be equal to 0, greater than 0, less than 0, or equal to f prime c. Well, we know that this is a local maximum, right? So let's draw I don't know what's happening, but let's draw a parabola. It doesn't have to be a parabola, it's just a curve with a thing that we know is concave down. Oh, sorry, spoiled it. We know that this is a local maximum, right? And if you look at the slopes of the tangent line, they are slowly but surely decreasing. They start off very positive, they become slightly less positive, until they become 0, after which they start actively decreasing and becoming more and more negative. So the slopes of the tangent line, or the first derivative, is decreasing, which means that f double prime, c has to be less than 0. We'll check, and we are correct. Okay, this one's funny. We have the derivative of arc cosine sine. I mean, not arc cosine cosine. It's arc cosine of cosine of x. So these are opposite operations. I keep putting the x. Inverse operation, so arc cosine cosine, these cancel out. You're left with x. So you get the derivative of x, which is going to be 1, as we've said. So that's, fun. And now let's go further. We have wrong notation for the derivative. Well, I mean, doesn't hurt to practice what we preach. dy dx, that is the correct derivative of y with respect to x. F prime x, that is the derivative of a f of x, function of x. Y prime, derivative of y. Y will usually be defined as a function of x. Then we have dy. dy, again, dy dx, not dy dx, or just dy or dx. These points by themselves actually have no meaning. I think I said, maybe I didn't explain why I made this channel, but this was actually one of the reasons why. Somebody asked me what dx meant, and they were a calculus BC student, so they've been doing pre-calc, calculus AB, and calculus BC. So, I mean, no offense to that person, obviously. I felt so sad. I felt genuinely somewhat sad because, I feel like they've just been failed. Dy and dx is respect to y and respect to x. When you differentiate or do d, differentiate with respect to y, or dy, so ddy or ddx, you are looking at a function that takes y as an input, and then you are finding the instantaneous rate of change, or the slope of a tangent line of that function that uses y as an input. So dy is respect to y, but it doesn't mean anything by itself. So, yep, that is the one that does not work. Y prime again works because y will equal f of x, or y will be a function of x. So if you do derivative of y, you will get that derivative of a function of x. F prime x works. F of x is explicitly defined as a function of x because f of x, function of x, and so you did prime or derivative of that, and then dy dx is just derivative of y with respect to x. Okay? And let's see if we got that right. We did. Okay, we guess. Alright. So, this is a interesting question we have. Considering f prime x, or f double prime, x is equal to 0, what does that tell us about that critical point? We talked about what would happen if the derivative is equal to 0 and the graph is concave up. Right? If the graph is concave up, then we can say, oh, this is relative minimum. And if the graph is concave down, we can again say that would be relative maximum. But if we don't know whether the graph is concave up or concave down, then it is neither. Or, well, at that specific point, we don't know if it's neither. So we simply say that the test fails, and we have to do something else. I know it's a sad way to cop out, but we just can't do the test for that. And let's see. This is a graph problem. We can kind of sketch it. So we have this, and then that point is 0, 3, and then this point is 2, negative 1, and it's asking which of the intervals is, let me fine, I'll graph this normally. Then this is 1, 0, and I think that will be enough. Oh, actually, no. That is not asked. Sorry. you're only given these 2 points, and it's telling us, well, it's asking us, the graph is concave down at which of the following points? Well, we have a relative maximum at 0, 3, and we have a relative minimum at 2, negative 1. So if we have a relative maximum, that means that f double prime is concave up, or concave down, and if we have a relative minimum, that means that f double prime is concave up. So, since we are asking for what's concave down, our answer will be 0, 3. Okay, we got that correct. And yeah, now we have another concave up, concave down type problem. We have x cubed minus 3x squared plus 3. When is this concave upward? So we have f of x. We need to do concave up or concave down. So concavity will be second derivative. So f prime x, n equals 3. We can pull that out. We have 3 times x to the 3 minus 1, or 3x squared, minus n equals 2. We can pull that out. 3 times 2 is 6, times x to the 2 minus 1, or 1, plus derivative of a constant is 0. So derivative of 3 will be 0, and this is our first derivative. Now our second derivative is going to be f double prime x, and so n equals 2. We can bring that out. 2 times 3 is 6, times x to the 2 minus 1. And we said that derivative of x is 1, so we have 6x minus 6, right? Okay, and we are asked when this graph is concave upwards, so when does f double prime x be greater than 0? So we add 6 to both sides, and we are left with 6x is greater than 6, which means we can divide 6 by both sides, or we can divide both sides by 6, and we will get a x is greater than 1. And then it just gives us a couple points, negative 1, negative 1, 0, 3, 1, 1, and 2, negative 1. 2 is the only x value that is greater than 1, so that will be the only point where f of x will be concave upward. And we got that one right. Okay. And this one is the exact same problem, but just very slightly different. It is not asking us when the graph is concave upward. It is just asking us when f double prime x is equal to 0. So from here, same thing, we add 6 to both sides. So 6x equals 6, which means that x equals 1. For the same reason, okay, oh, sorry. I mean, it's a very similar problem. I guess I just didn't look at it correctly. This is x cubed minus 3x plus 3. And now, derivative of x is 1, so this will be minus 3. And then derivative of a constant is 0, which means that this is 6x equals 0. Divide by 6 on both sides, so x equals 0. We didn't actually do any derivative stuff wrong, I just misread the question. Okay. Okay, we're going into some interesting stuff. Okay, so actually not sure if we should do this one. Actually, no, let's not do that one. That one uses a lot of notation. So, this one's an interesting one. We have, this one's going to talk about roots. We have x cubed minus 3x plus k equals 0. And you have to find the values of k, with which there are 2 roots on the interval 0 to 1. So let's do the derivative. We'll have 3x squared minus 3, as we did, n equals 3, pull that out. 3 minus 1 is 2, so we have 3x, 3 minus 1, so 2, minus derivative of x is 1, so 3. Then from here, y prime equals 0, so let's let this equal 0. we'll have x squared. Well, we can 3x squared minus 1 equals 0. We can divide both sides by 3. We'll have, well, I could have put this 3 to the other side, and that might be a little bit easier. But we'll have x squared minus 1 equals 0. So x squared equals 1 when you put them 1 plus 1. And then x will equal plus or minus 1 when you do square root of both sides. And these points, 0, 0 to 1, this is parentheses, so it's not inclusive of this positive 1, which means that k, there are no values of k that satisfy this because the roots will be negative 1 and positive 1, and 1 does not get included when you have open parentheses. Okay? Okay. So we have particles moving on y equals, let's see if we can do this, y equals x squared plus 2x. Wait. Oh, this is a related rates problem. Okay. We could do this. I think we could do this, actually. So, related rates is when you have two separate quantities, right? Y and x, and you have to differentiate with respect to a complete different variable. This one is going to be time. This is a particle is moving. We should do some related rates problems after this. Particle moves along y equals x squared plus 2x, and then the points on the curve, x and y, these are changing at the same rate with respect to time. So we have to do the derivative of y with respect to time, and then or not respect to time, it could be respect to t or whatever, but I'll think of this as respect to time, and then we'll have to do the derivative of x with respect to time. And these two are equal, right? Because y is a function of x, and y equals x squared plus 2x. So the derivative of y is the derivative of y with respect to x is the derivative of y, and y is equal to x squared plus 2x. So the derivative of x with respect to t is the same as the derivative of y with respect to t. And so from here, we can do the derivative of x squared plus 2x. So that would be 2. We can bring that out. Derivative of x is 1, so we have y dy dt is equal to 2x plus 2. I actually don't really like this problem. There are a lot better examples of related rates that we will probably need to do, but we do need to make 2x plus 2 equal 1, right? Because dy dt has to equal dx dt, and if 2x plus 2 dx dt equals dx plus dt, that means that that's the same as 1. So for this, minus 2 minus 2, 2x equals negative 1, x equals negative 1/2, which means that our point is, when you plug it in there, let's plug it in there, we have negative 1/2 squared, which is 1/4, minus 1/2 times 2, so negative 1. So you have negative 1/2, and then negative 3/4. But I don't like this problem. I'm going to search up some related rates problems, and we're going to do some of that. Okay, so I just searched up related rates word problems, found the first one. One car leaves a given point and travels north at 30 miles per hour. So let's say it travels north at 30 miles per hour, and then another car leaves 1 hour later and travels west at 40 miles per hour. So we'll say that west looks, never read soggy waffles, west is like that. If that's north, that's west. Let's put that back. And then what's the rate of the distance changing between them? So let's say that this is x and this is y. X is the rate at which the first car is traveling north. So we can say that this is dx, or the change in x's position with respect to time. And we are measuring in hours. I think hours is appropriate. So this is going to be 30 miles per hour. And then we have dy dt, or the rate at which y's position changes with respect to time. It's 40 miles per hour, right? 40 miles per hour. And we have to see how the distance between them changes with respect to time. So, and this is after 2 hours. So when t equals 2, we have to see what this looks like, right? So let's do, is this? Oh wait, no, this is integrals, right? Yeah, this is integrals. Well, I guess I'm gonna finish this problem because I started it, but don't worry about this. I should have done this in my practice video. Ugh, I didn't do enough practice, even though 4.5 hours I thought was excessive. But practice never hurt anybody. We will integrate with both sides with respect to t. So if we assume that these are functions of t, we'll have this is equal to y is equal to 40t, and then x is equal to 30t. Yeah, I just had a complete brain malfunction. I forgot that we are doing derivatives and not integrals, and related rates is definitely integrals, but uh, we kind of, we do, right? Oh wait, let's see. I guess this kind of uses derivatives too. Okay, so let's go to the Pythagorean's theorem. We have, this is z squared. We're trying to see how this changes with time, not z squared, but this is z. This is the hypotenuse. And we have to see how this distance between the car that's traveling north and the car that's traveling west, we have to see how this distance changes with time. So if we know that x squared plus y squared equals z squared, okay, wait, no, this uses derivatives. This is valid, and this is 32. I wrote that. So you have to differentiate all of this with respect to t, right? We have the positions, but now we need to see the positions with respect to time. We need to differentiate. So we have the derivative of 2, or x squared. You can bring that 2 out. You'd have 2x dx dt plus 2y dy dt equals 2z dz dt. And what we're trying to find is the change in the distance between them with respect to time. So we're trying to find dz dt. So let's plug in everything that we have. We have x is equal to, what is x equal to? Oh, well, we know that x is equal to 30t, right? So if t equals 2, x equals 60. They must have traveled 60 miles, and, this started 1 hour later, 40t minus 1. So when we plug in 2, we'll say that this is 40, right? So t equals 2, x equals 40. T equals 2, x equals 40. And so let's just kind of plug in everything that we have so far. We have 2 times x, which we said was 60. 2 times x, which is 60, times 30, right? So dx dt, which we said was 30. And then we have 2y, so 2 times 40, 2 times 40, and then we said that this derivative was also 40t. So 2 times 40 times 40 as well. And then this is equal to 2z dz dt. So if we plugged in 30 and 40, oh, wait. Oh no, this isn't a golden triangle. I thought this would be nice and simple. We have to do Pythagorean's theorem. So we have this x is equal to 60, this y equals 40, and so we'll have 60 squared plus 40 squared equals z squared, so square root of that, and I do not have a calculator. 1 second. Okay. I do have a calculator, so we have square root of 60 squared is 40 squared. That would be 72.111. 2 times 72.111. 2 times z times dz dt, which is what we're trying to find, right? And then we can solve for dz dt. So we solve for dz dt, and we get we get 47.15 dz dt, or the derivative of z, or the change in z's position with respect to time, is equal to 47.15, or 1.50. So what did we do, right? We saw two variables. We observed a relationship between those two variables, and then we are trying to find the derivative, or the change of, like, that relationship between these two variables with respect to time. That's what we are doing. Or it doesn't have to be time, it can be respect to anything, but most of the time it will be time. That was an interesting sentence, but you have to have two variables that are different. You observe a relationship between those two variables. You do the derivative so that you can see how this relationship changes with respect to time, or with respect to x, or with respect to position, or whatever, and then you solve for something. You either solve for the time itself, you solve for the change with respect to time, or something is happening that you are solving for. But yeah, you find a relationship between two variables. So my usual methodology for this is draw a diagram. You can be the worst artist in the history of humanity. It does not matter. As long as you draw, it works for me. But if you draw something, you can kind of visualize what is happening. So draw something, draw a triangle or a circle or whatever the question's asking. Draw something and come up with like a visualization of what is going on, right? What is changing, what is supposed to be changing, and what is the relationship between these two variables? We had x squared plus y squared equals z squared. That north and west, those were two legs of some right triangle. So we can just use Pythagoras theorem. That's the relationship that we observed. If you have like a circle, for example, then you can have pi r squared, or diameter pi. But you need to remember, you have two variables with some type of relationship with one another, and then you have to differentiate with respect to some other variable. It could be time, it could be x, it could be position, it doesn't matter, but you are differentiating with respect to something else, and then you are solving for whatever the question is asking you. So we can do another one of these things. I'm just going to finish a couple more of these examples. It is a little bit late. I think I might have to concede and say that I'm going to go to sleep at a reasonable time and not do another extra hour. Well, I'm going to finish this hour so we get to 3 hours, but I don't think I'll be getting to 4 hours. Don't worry, I will achieve some goal at some point, but I'm just going to finish more of these, what's it called, related rates examples, because they are important. So, next question, a 50-foot ladder, so it has to be at some kind of an angle, right? A 50-foot ladder is placed across a building. So let's imagine a building goes out like that, and it is 50 foot long, right? And the base of the ladder is resting on an oil spill, and it slips at a rate of 3. So we can call this y, um, this ladder is slipping at a rate of 3 feet per minute. Find the rate of change of the height, we'll call that height x, of the top of the ladder above the ground at the instant when the base of the ladder is 30 feet. So when the base is 30 feet. Okay, so what is it asking? It's asking for the rate of change of the height. So if x is the height, we are trying to find the rate of change of the height. So the change in the height's position with respect to time. So dx dt at time equals, or not when time equals, but when y equals 30, or when the base of the ladder is 30 feet from the base of the building. So 30 feet, so when y equals 30. Again, this is going to be a triangle. Now we have no z. We're only trying to find dx dt. So let's write what we have so far. We have x squared plus 30 squared equals 50 squared, right? We know what 30 squared is going to be. And using our golden triangle ratios, we have 3, 4, 5. Any multiples of 3 and 4 will have a multiple of 5 as a hypotenuse. And you can, interchangeably switch those around, but only when your legs are multiples of 3 and 4 and your multiple is and your hypotenuse is a multiple of 5. So this one will be 40. And from here, now what we have to do, let's write our formula so far. We have x squared plus y squared. We could write this as a 0. I mean, x squared plus y squared equals z squared, though. Z doesn't actually change. So, let's see how we would do this. Let's say this is 50. And so we have 2x dx dt plus 2y dy dt equals 0, right? And then we know what x is equal to. That's 40. What is dy dt equal to? Well, the dy dt is supposed to be 3, right? Dy dt is equal to 3. And let's see. Now we have to find dx dt. So if dy dt is equal to 3 and y is equal to 30, or 30, let's solve for dx dt. So we'll just bring that 2y to the other side, or 2y dt. So we'll have 2 times, what was x, 40. So we have 80 dx dt is equal to 2, or negative 2 times y, so negative, what was, negative y, so negative 2 times y will be negative 2 times 30, which is negative 60, and then that will be dy dt, excuse me, so it's negative 60 times dy dt, which we just said was 3, and then we're dividing both sides by 80. So 30 and 40, right, because both of these are multiples of 2, or, well, you could probably go a little bit further than that, but actually, we should go further than that. Let's say we can divide both by 20. So you'll have 3 and 4, and you'll have negative 9 over 4, negative 2.25. And that will be feet per minute. Because this is a rate, right? The change in x's position in feet per minute. Now let's try to interpret this within the context of the problem. There's an oil spill, right? Let's try and draw an oil spill. I draw it, it just looks like a circle. Let's kind of, sure, that's an oil spill. And this ladder is slipping down. So this is decreasing, right? And this rate as this y, the distance from like where the ladder is touching the ground at the base of the ladder, and it's quote unquote distance from the x, but just like where the ladder is touching the ground, it's getting further and further away from the building, right? Yes, that's like the roof. I'm not gonna draw a building, you know what a building looks like, but as this ladder gets further and further away from the building, the top of the ladder, or the highest rung, will get closer and closer to the ground. It will fall because the base is slipping away, right? So that's what it means. Like, just, I don't think there will be a related race problem that just doesn't make sense. Because when you are given a related race problem, you draw it and you understand what's actually happening. Again, let's review. You are trying to make a relationship between two variables, and then you're going to differentiate both of those variables with respect to another variable, usually time, and then you find some missing value. That's all related rates is. And we can do, a couple more of these. We have a stone dropped in a pond sends out a circular ripple. So let's have a little stone, and then, it sends out ripples. So let's have one ripple that just extends outwards, right? And the radius increases at a constant rate. So let's call this r. Constant rate of 4 feet per second. How rapidly is the area increasing? So we have dr dt, so the rate of change of the radius with respect to time, and that is equal to 4 feet per second. Right, and now we have t equals 12 seconds, and we have to find dA dt, or the change in area with respect to time. So let's do so. We have, we have dr dt. So if a equals pi r squared, we have, we're trying to find dA dt, right? So we have to do, derivative d dt on both sides. So we're going to have pi, we'll have 2 pi r, actually. Again, you can actually write this as d dt of r squared is equal to ddr of r squared times dr dt. So this is just another application of chain rule. Same on this side, but the derivative of a with respect to a is just 1. So, we have that. So this is 2 pi r dr dt. Now we know what dr dt is equal to, right? It's 4. So we have dA dt is equal to 2 pi r. So 8 pi r. 8 pi r. And we said that t is equal to 12 seconds, right? So at 12 seconds, the r, obviously at 12 seconds, this is the rate of change of the radius, for the radius is increasing by 4 every second, and after 12 seconds you will have traveled 4 times 12, or 48 feet. So you have 48 for r, 48, and 48 times 8 I think will be like 384, because 320 plus 64 is 384, so we'll have 384 pi per feet per second, sorry. And actually this will be feet squared, right? We're doing dA dt, so we're seeing the change in area with respect to time. And these ones aren't particularly, well, I don't think they're too hard. I think they make sense, and you just think about the context of the problem, and you continue solving from there. But, we have a couple more. This one's a sphere. A spherical balloon is being inflated, so let's try and draw a balloon. That's not a sphere, but whatever. A spherical balloon is being inflated so that its diameter So if we kind of draw that, that's like the way that you would draw this. So that's the diameter on the inside. The diameter of a sphere is increasing at a rate of 2 centimeters per minute. So dd of dt is equal to 2. But I actually don't like that. I want to express d in terms of r because the area of a sphere, the volume of a sphere is written in terms of r. So I will say that d is equal to 2r, which means that, well, if d is equal to 2, then r will equal 1, right? So if we write dr dt, we will get dr dt equals 1. And so if we are trying to find, oh, and the question is asking, how quickly is the volume of the volume increasing when the diameter is 10 centimeters? So we have dv dt when diameter is equal to 10, or when r is equal to 5, right? Because d over 2 is equal to radius, and then radius will be equal to 5. So now we have to find, well, let's look at the relationship that we have. We have the volume of a sphere, so that will be 4/3 pi r cubed, and we have to find the rate of change of the volume with respect to time, so dv dt, and so we multiply that 3 out there, and again we're doing chain rule of this r cubed. We're doing d dt of r cubed is equal to ddr of r cubed, so differentiating r with respect to r, and then multiplying that by dr dt. So when you bring that 3 out, 3's cancel, so you'll have 4 pi r squared, and then multiplied by dr dt. We said dr dt is 1, so I'll just kind of scratch that out. And then this 5 squared will be 20, right? And then, let's see, okay. And then we have, wait, what did I do? Okay, so, oh, sorry. Yeah, it's late. If it's not obvious, we have r squared is equal to 25, right? We have r is equal to 5, so r squared will be equal to 25, and then 25 times 4 is 100. Yeah, I do need to go to sleep in a reasonable time frame, so we have 100 pi cm cubed per minute. Again, we're doing change in volume, so dv dt, that's what I meant to circle. So change in volume with respect to time. I'm hoping that you see that related rates aren't too bad. I know that we're doing some relatively simple examples, but I will continue this example video tomorrow, and we will do some more advanced related rates problems, and perhaps more advanced derivatives in general. But let's just continue on the rest of this worksheet, and hopefully we'll finish it. So we have the radius of a cylinder. Let's draw the cylinder. We have, draw the base. Not the greatest cylinder. Let's do that one more time. We have the base. We'll draw like that. Sure. And that will be R. Let's draw that center point. This is R. And the radius is increasing. So dr dt is equal to 1 positive. And the height, so h, is decreasing. We have dh dt will be negative. It's decreasing, right? So if the derivative is negative, we are decreasing. That same rule carries over to related rates as well. It is decreasing at a rate of negative 4 meters per hour. At a certain instant, the base radius is 5, so r equals 5, and the height is 8, so h equals 8. Okay, and what is the rate of change, dv dt, at that instant? So v equals pi r squared h, again. This is base times height, but we just have the base is a circle. So, that's a pretty cool way of thinking of this. I mean, my mind was blown when I learned that, but I suppose most of the people watching this have known that. But DVDT, we will have to not integrate, differentiate with respect to t. So derivative of v, derivative of x is 1, so derivative of v with respect to v will be 1, and you have to multiply that by dv/dt. Pi is a constant, not changed, r squared, n is equal to 2, we can bring that out, and then 2 minus 1 is 1. So we have 2 times r to the 1, or 2r, so we'll say 2 pi r dr dt, and then this will be multiplied by h, right? We have to do product rule. We have to do the derivative of this plus that times the derivative of that. So we have 2 pi r times dr dt times h, and then pi is a constant multiplied to all of this. So this derivative, you have to distribute that pi, and then we have to add that pi r squared times the derivative of h with respect to h. The derivative of x with respect to x is 1, so the derivative of h with respect to h is 1, but we still have to multiply by that dh dt. Remember, this is just ddt of h is equal to ddh of h times dh dt. I know you're getting a little bit sick of me saying this over and over, but it is important to remember. And now we have a bunch of information to plug in, right? We know that 2 pi r, we know that r is equal to 5, so 2 pi r will be 10 pi, and then dr dt is 1, so we can say that this is 1 times h, which is 8, and then pi r squared, r is again 25, or r is 5, so r squared will be 25, so we have 25 pi times dh dt, negative 4, so we will have, wait, does that make sense? I think that makes sense. Yep, that seems fine. And then we have 80 pi minus 100 pi, so like 10 times 1 times 8, so 80 pi minus, so 25 times negative 4 will be negative 100. So we'll have 80 pi minus 100 pi, which is going to be negative 20 pi meters cubed per hour. Again, we're doing change in volume with respect to time. And yeah, I mean, we found a relationship between our variables. We differentiated everything with respect to a common variable, and then we found whatever missing information we needed to find. Related rates has a very, pun intended, very simple formula that you just need to follow. And let's keep going. We have, one last question. A person who is 6 feet tall, let's draw, or try to draw. A person is walking away from a lamppost that is at the rate of 40. At 40, we'll call this x, the distance, at a rate of 40 feet per minute. When the person is 10 feet from the lamppost, or when x is equal to 10, their shadow is 20 feet long. Is that how it works? Oh no, it's like, it's this, right? One second. So when the person is 10 feet away from the lamppost, his shadow is 20 feet long. Find the rate at which the length of the shadow is increasing when he is 30 feet from the lamppost. Okay. Wait, does the lamppost have any effect on this? Interesting. Okay, so let me actually redraw this a little bit. So we have a lamppost, right? We'll draw that lamppost up here. I'm not gonna be, too artistic about it, but this is a lamppost, not a hairy stick. So with this lamppost, we have another person that's over here, and this person casts a shadow that is 6 feet. We'll let that 6 feet be over there. And this person is X feet away from the lamppost at any given moment, and they are 6 feet tall. So, yeah, now, where? Oh, now we need to find height. What's the height of this? And then we are trying to find the rate at which the length of the shadow, S, is increasing when X is equal to 30. Okay, so we have ds dt. Now we need to just find H. And, we can solve for X and stuff. But this is a similar triangle, right? We have this triangle and we have this triangle, and those are similar triangles. So, or well, not that triangle, this triangle, all of it, and then S plus, and this triangle and this triangle. Those are similar triangles. I didn't draw it correctly, but they're supposed to be. So that means that X plus H, this ratio of this side, or one base to the other base, is going to be X plus S over H, should equal S over 6. These are similar triangles, right? So the height of the pole will not change, so we can keep that the same. And we know that at this point, X is 10, the person is 10 feet away, and then S is 20. I really didn't draw this correctly. That the way that the shadow is supposed to be drawn is much different. But it's whatever, as long as you kind of know what's supposed to happen. So we're going to have 10 plus 20 over H is equal to 20 over 6. So this will be 30 over H equals 20 over 6, which means that when you cross multiply, 20H is equal to 180, which means that H will equal 9. So if H equals 9, we can replug this back into our formula. We have X plus S over 9 is equal to S over 6. And then, we can cross multiply again, bring that there, bring that there, and then we'll have 6x plus 6s is equal to 9s. 6x plus 6s is equal to 9s. So we subtract 6x from both sides, 6s from both sides, so we get 6x equals 3s. And now we just change, we see the distance, the change in x, so change in how far the person is with respect to time. So derivative of x with respect to x will be 1 multiplied by the derivative of x with respect to time. So we'll have 6 dx dt is equal to the rate of change of the shadow with respect to time. So derivative of s with respect to s is 1, and then multiplied by the derivative of the shadow's position with respect to time. So ds dt. And we know that dx dt, what did we say dx dt was supposed to be? Oh, yes, dx dt is supposed to be 40. Dx dt is supposed to be 40, which means that if you plug that in to 6 dx dt, you will have 6 times 40, so 240. And then you divide by 3, so you get ds dt will be equal to 80 feet per minute. So yeah, I hope that's not too bad. Like the related race problem, they do fall into that same kind of rhythm. You find some relationship between variables, you differentiate, and then you find whatever's missing. That's all you need to do. And it's honestly not too bad. Um, they usually give you the formula if it's something very complex, but most of the time you're working with like prisms and trying to find volume or surface area, so things that you know, and you're just finding the volume with respect to time, or like the length of a base with respect to time or something, and you differentiate. It's honestly not too bad, like it's just chain rule, different application of chain rule. I had a very difficult time reminding myself why dx, why you have to multiply by that ds dt, but I think it makes sense. Like that dv dt, it's not just a placeholder, right? You're actually dv dt is actually v prime. So v, you're doing ddt of v, right? This v does not just, distribute to that d. What you're actually doing is the derivative of v with respect to v times dv dt. You might think that this distinction isn't really important as long as you know what it's supposed to look like, but that's kind of why this channel was made. To understand what you're doing instead of how you're doing it. So dv dt is just the derivative of v with respect to v times the derivative of v with respect to t. And then v, like x, that derivative with respect to x is 1, so the derivative of v with respect to v will be 1 times dv dt. So that's what this is happening. That's what that's what this is happening. That's what that means, and it's important to know that. And it's important to know some of this. Well, I think it's important to know that. I think it's important to understand what you're doing, to see the chain rule, and to see applications of it, so that you don't forget it. It's obviously very important for calculus, and isn't it good to just kind of know? Like, maybe it's just me. I don't think it is. I think everybody has that latent curiosity, but I'm of the opinion that, you know, everybody's a little bit curious about what they're doing. It could be math, it could be anything that they're doing, but don't you just feel odd if you're kind of just doing to do? I don't really like it, but if that kind of learning works for you, then it works for you. No questions asked. I just think that it's a lot more helpful to know what you're doing and why you're doing it, to actually, want to do it and to do it correctly. And just to, finish off everything, I found a really fun problem. So, you have to find a derivative where f of x, so you have to find f prime 3 pi over 2 where f of x is equal to sine x plus 1. This is more like for fun. I don't think you need to know this to the power of x. And then you can go to limit definition. There are some points where you might want to use limit definition. I know this is a kind of random transition, but I really like this problem when I saw it. So then we have the limit as h approaches 0 of f of 3 pi over 2 plus h minus f of 3 pi over 2. I will do this tomorrow, but I'm definitely going to forget this. I just saw it. Over h. And then, sine of 270 plus h, or 270 plus x, is equal to negative cosine x. This is just a, relationship. If you draw your unit circle and say this is some angle of x, then if you go 270, right, that's 180, so 270. So say you're doing sine of that, now you would actually be doing cosine, right? If this is a 90-degree angle and you were doing this is complementary to that, so the sine of this will be the cosine of that. So, Sine of 3 pi over 2 plus h will just be negative cosine of h. Not cosh, but you know. And then, so we'll have negative cosine over h, negative cosine of h. Well, oops. So from here, we just plug in our f of x. So we'll have the limit as h approaches 0 of 1 minus cosine h 3 pi over 2 plus h all over h. And now f 3 pi over 2 is equal to 0. We can do that unit circle real quick. You have negative 1, 0. So if you draw a line with height 0, 1 there, 1 there, radius will always be 1. Opposite over hypotenuse, 0 over 1 will be 0. So from here, you have this very nice limit, and we need to do that squeeze theorem, right? We know that 1 minus cosine h must exceed this because, this is a fractional exponent, 3 pi over 2 plus h. So this must be greater than 1 minus cosine h, 3 pi over 2 plus h, and then is less than 0. And then, since 1 minus cosine h, we'll write that down, is less than 1, and 3 pi over 2 is going to be greater than 1, then since the derivative of the cosine function is negative sine, we have 0 is less than or equal to the limit as h approaches 0 of 1 minus cosine h. I might need to erase some of this. 1 minus cosine h to the power of 3 pi over 2 plus h all over h is less than or equal to the limit as h approaches 0 of 1 minus cosine h. And, as a nice kind of bow on the end of things, we have another squeeze theorem. The limit of this equals the limit of this. We worked on this at the very beginning. This is 0, and so this limit must evaluate to 0 as well. That means that f prime 3 pi over 2 is equal to 0. I don't really know why I showed you this. I just like this. It's a pretty cool example of using limit definition of derivative. It's a interesting looking answer, and it uses squeeze theorem, which I think should be used more often. It's pretty cool. So yeah, that was some practice of derivatives. I will do more. I need to fulfill my promise of 4.5 hours. We did some 3 hours or so today, so we do have quite a bit of work ahead of us, but we can push through, persevere, embrace the struggle, etc., etc. And yeah, now it's time for an album recommendation. It took me quite a while to find one last time. Can't recommend Rina Sawayama again because, it's a cop-out. I have been listening to Love Island, not the actual show, but the album. What have I been listening to? I have been listening to quite a bit of Hiatus Coyote. I'm not sure if I actually recommended them or not. They are very good. I think I have recommended Mood Valiant. It's definitely their best album. In my opinion, Choose Your Weapon was definitely good, but Mood Valiant, all of their ideas are more fully developed, and the instrumentals are a lot better. The voice is a lot more, I wouldn't say, advanced or anything, but it's definitely a lot more developed. I don't want to keep repeating myself, but they really just came through on that album, and you can hear it. Um, been listening to some Jid at least recently. Yeah. I listened to that Imagine Dragons track with him. That's I don't know why Imagine Dragons still releases music. I mean, no offense to any Imagine Dragons fans out there. Like, live your life, have fun, don't care about what I think. But, the fact that they're actively still creating music, it kind of surprises me. It's kind of like, if. It's kind of like Soldier Boy continuing to release music, it doesn't feel real. But I mean, if other people don't consider their like style somewhat dated, and they still have enormous commercial numbers, then who am I to judge, right? But I did listen to that track, and I thought it was just a touch, too much for me. But let's see. I've been listening to a lot of Sour, Olivia Rodrigo. I mean, everybody knows that album, but I do really like it. Um, yeah, I've just been listening to a bunch of like pop. Man, I wish Sawayama came up with more music that I can recommend, but I can't. Let's see if I listen to anything on other stuff. Wait, I honestly. Wait, okay, okay. Here we go. This is not a cop out answer. I think I have a really good recommendation because I don't think I like recommended them at all. And that is sometimes I might be. I'm so happy I found something. Sometimes I might be, and this is okay. This is carrying over to tomorrow. All right, this is carrying over tomorrow. I'm keeping this. This is my same album recommendation for the rest of this video. Right. This is not a cop out answer. Sometimes I might be introvert by Little Sims. Ugh, what a wonderful album. I mean, I mean, it's just, it's really good. Uh, Instrumentation's on point. She just has so much energy, and it's like so deeply personal, and like you really you get this feeling that she there's this like split between the first and latter half of this album. Like you just have this very timid and like self-contained, slightly more bare instrumentation, a little bit less, crazy. But towards the latter half of the album, she like grows into a little bit of an acceptance of herself, and then she just grows more, energetic, but still keeps that somewhat like detached, aesthetic quality to it. I mean, like Point and Kill, had that on repeat. Fear No Man is really good. Introvert, like the opening track, is very good. Um, Honestly, it's a very solid album. I don't think there's anything that's particularly bad. Um, Lots of people have been saying that this is a 10 out of 10 album. On that front, I think I'd agree, just understanding that I don't remember any songs that I would consider bad. Like, if I were to listen to every song through, I would, not be bored. There were a few, like, points that weren't as memorable as other songs, but, you know, every song is good. There's something to enjoy in every song. So on that metric, maybe it would be considered a 10 out of 10. But this is just a great album. Listen to it if you'd like. I'm so happy I finally got an album. I feel like I've just been, random. But yeah, no. I Love You, I Hate You, Little Q Part 2, Point and Kill, Fear No Man. All of them are good. Speed was also good. And also, she like has. I mean, I'm not prude. I'm okay with profanity, but she knows how to temper it. And it's kind of like this is a really, really weird analogy. It doesn't even remind me of this movie. Just the like way it's used. I guess it's just because I watched it the other day. But Joker, you know how there's like only 4 gunshots in that movie. It is a pretty violent movie, but there's only 4 gunshots, and they just seem so much louder and so much more like surprising. So yeah, like every curse word, it's not like a gunshot or anything, but everything, it's not particularly surprising because they do fit in with the rhyme schemes and they make sense within the context of certain songs. But since she uses her words very sparingly and knows how to manipulate her words to do what they want, do what she wants them to do, when she curses, it just draws her attention a lot stronger than other words. But very good album. Definitely would recommend. Most of her discography is pretty fantastic. I don't think she's had a bad album by any means, but listen to this. It's very good. And yeah, if you like this video, please comment down below. If you did not like this video, I will have another hour and a half to redeem myself tomorrow. But regardless, you can comment down below. Constructive criticism is always encouraging. If you're not in the mood for constructive criticism or a comment, then I don't know. Um, do some wall sits. I think I've already done that one, but it's a good exercise. It's really good for strengthening your knees. I got pretty bad knees, so I have to do wall sits a lot. But yeah, all right, bye.